Okay, so we talked last class about eigenvectors, and we learned. I mean, what is an eigenvector? Well, if we think about the definition for an eigenvector, okay, hold on here. I'll plug this little thing in here. Okay, so an eigenvector x is a solution to this matrix equation. And the matrix A is square, it's an n by n. The vector x is n by 1. Lambda is a scalar. The vector x is n by 1. And also, x is not equal to the 0 vector. Okay, the reason we do that is because, if you were to take a times the 0 vector, that would equal lambda times the 0 vector, right? So that's not a very interesting vector. The eigenvectors that we talk about are non-zero vectors, and they are solutions to this matrix equation. Now, eigenvectors have a lot of properties and applications. Some of you have already seen them in differential equations when you solve a linear system of differential equations. We're going to see other applications as well. And like in section 5.1, what you were given was problems where they gave you, like we had a problem where they gave us an eigenvalue, and we had to find a basis for the eigenspace. But what if you're not given? This eigenvalue? What if you're not given the eigenvalue? How do you find the eigenvalues? Well, the answer is we have to solve an equation called a characteristic equation. Okay, so if we look in the book here, section 5.2, okay, they have a 2 by 2 matrix, A, here in example 1. 2 by 2 matrix, and they want you to find the eigenvalues of the matrix A. Now they're saying that we have to find here, that we have to find all scalars such that that matrix equation, A minus lambda I in parentheses times the vector x equals 0, has a non-trivial solution. Okay, well now let's go back to the whiteboard here. Okay, and remind ourselves where that comes from. So if you have A times x equals lambda x, and we're assuming x is not equal to the 0 vector, x is the eigenvector, lambda is the eigenvalue, you can write A times x equals lambda times an identity matrix times the vector x. Because if you take the vector x and multiply it by the identity matrix, you're going to get the vector x. So now what you can do is you can subtract this term to the left side, and then you can factor out the vector x on the right side. And remember, the vector x is not equal to 0. So solving this matrix equation, which represents a system of equations, okay, is equivalent to solving this matrix equation, which is a homogeneous system of equations. And I mean, it's an equivalent system. So in the book, in example 1, they say we must find all scalars such that this matrix equation is true. And there's a reason they use that. So if we go back to the book, so that's just review really. Okay, so how are we going to find the eigenvalues? Okay, they have a statement here. They say by the invertible matrix theorem in section 2.3, this problem, okay, solving that matrix equation, okay, is equivalent to finding all lambda such that A minus lambda I is not invertible, where they have the A minus lambda I. And they also say by theorem 4 in section 2.2, the matrix fails to be invertible precisely when its determinant equals 0. Oh wow, how'd they get the determinant in here? Well, these comments in example 1, I'm going to justify those comments to you. You should know why they're true. But for now, let's just go ahead and solve this, what they call a characteristic equation. Okay, so let me just highlighting as we go along. This here is known as a characteristic equation. When you take the determinant of A minus lambda I and set it equal to 0, that's called a characteristic equation. And what you can do, it's an equation. And you're going to get, well, you know how to compute the determinant of a 2 by 2. And what's going to happen is you're going to get this polynomial equation here, which it turns out can be factored. So the determinant of A minus lambda I is equal to lambda squared plus 4 lambda minus 21, and that factors into lambda minus 3 times lambda plus 7. Well, this means that lambda would have to equal then 3 or 7. So those are your eigenvalues. Okay, so that's a very simple example. And again, what we did here, if I just go down a little bit, is we used the characteristic equation, which is the determinant of A minus lambda I being set equal to 0, to get the eigenvalues. Okay, now it's really, I think, important to have a good understanding of why that works. Okay, so let's have a little discussion here. Let's have a little discussion. Let you put this in your notes. Okay, so take a moment to write this in your notes. Okay, so we want to show why solving this characteristic equation here will give us the eigenvalues, okay, of corresponding to a matrix A. And you notice in example 1, section 5.2, they quoted several theorems and all that. So, but let me show you what they mean. So here we go. So all right. So we wish to find all scalars lambda such that this matrix equation has a non-trivial solution X. And I already showed this, but this is true because this matrix equation, which is the definition of what an eigenvalue means and what an eigenvector means, is simply this equation down here, this matrix equation. Okay, so let me give you a moment to copy, and let me know, please, if you have any questions. Okay, so we start from this statement here. If you wanted to solve, okay, hold on here, if you wanted to solve this equation for the eigenvector x, okay, how would you do it? Well, if a minus lambda I is invertible, okay, if a minus lambda I is invertible, and we don't we don't know what values lambda is, but let's say we know that lambda will be some values, and if we had a specific value of lambda, multiplied it by I, subtracted that from A, we would have a matrix of values, a square by square matrix of values. So if A minus lambda I is invertible, we certainly could solve for X by multiplying both sides of this equation by the inverse of A minus lambda I. And it turns out then that X equals the zero vector. Okay, now do we want that? Do we want X to be equal to the zero vector? That's right, David, that's right, Mikhail. We do not, because an eigenvector is a non-zero vector. So if the matrix A minus lambda times the identity is invertible, that means then that the vector X is going to equal the zero vector. Okay. Are there any questions before we go to the next page? All right. So all right, what do we know? What do we know? Well, we know that if A minus lambda times the identity is an invertible matrix, then X is the zero vector. Okay, but this is like, let me see here, let me phrase it the way I want to phrase it. Hold on. So I don't know, this might be the first time you've seen this, but this is like a statement P, and it implies a statement Q. Did you know, though, that if P implies Q, that's right, Mikhail, then not Q implies not P? That's called a contrapositive. If P implies Q, then not Q implies not P. That's called a contrapositive. How many maybe have seen that in another class? It's a logic statement. Okay, Mikhail saw it in 207, absolutely. Well, this means that if X is not equal to 0, okay, that means not Q, right? Then that implies not P. And that's what this is. That A minus I is not invertible. That's not P. Well, remember, by the invertible matrix theorem, if a determinant, if you have a matrix that's not invertible, well, I'm not sure I mean, there is a connection here. If you have a matrix that's not invertible, then the determinant of that matrix is going to equal 0. Okay, so like for an example, let's take an easy one. Let's say you had a matrix like this, 1, 2, 1, 2. Okay, is this matrix invertible? 1, 2, 1, 2. The matrix whose columns are 1, 2, column vectors 1, 2. No, that's not invertible, because if you take the determinant, well, let's use the notation we're used to. Okay, so if you take the determinant of that matrix, you know for a 2 by 2 how it works. You know how that works. So that's going to be 1 times 2 minus 2 times 1, and you get a 0. So anytime you have a non-invertible matrix, the determinant of A is equal to 0. Now, why is this matrix here non-invertible? Well, what can you tell me about the column vectors of this matrix? The column vectors are I'll tell you what, let me do another example. Hold on. Forget that example. Let me do a better one, okay? Let me do a better one here. Hold on. I got a better one. Okay, so say that your matrix is this. 1, 2, 2, 4. Is this invertible or not invertible? Okay, so that matrix is not invertible. How do we know that? How do we know that so quickly? Well, what can you say about the columns of this matrix? The vectors 1, 2, and 2, 4. What can you tell me about those columns? They're linearly dependent, absolutely. They're linearly dependent. And so by the invertible matrix theorem, this matrix is not invertible by the IMT, because we learned by the invertible matrix theorem that if the columns of the matrix are linearly dependent, then the matrix is not invertible. Well, now if you were to take the determinant of this matrix, you're going to get 1 times 4 minus 2 times 2, and that's 0. So that's just kind of an example I'm not saying it's a proof, but hopefully it'll convince you that, hey, yeah, if I have a matrix that's not invertible, then its determinant is going to equal 0. Okay. Now, in our case, we have the determinant of A minus lambda I is not equal to 0. And if the determinant of A minus lambda I, I'll put it in maybe black here, what's this called? What's this equation called? Remember the name? Can anybody tell me? I'm giving a lot of letters here. Determinant of A minus lambda I equals 0. What's that equation called? Look in your notes. You just copied it down. That's right, Mikhail. That's your characteristic equation. So essentially, from the definition of what an eigenvector is and what an eigenvalue is, but I mean, what we started from the definition, this basic definition here of what an eigenvector and an eigenvalue is. We started from this basic definition, and we ended up with that this definition implies then that the determinant of A minus lambda I equals 0. And that's the characteristic equation, and that's what we need to solve in order to find the eigenvalues. Okay, are there any questions? Any questions? Okay, if there are no questions, let's go ahead and look at an example here. Let me give you a moment to copy it down. And actually, for our purposes, I'm just going to say, let's find the characteristic polynomial of the matrix A. Because in your homework, they basically give you matrices and they want you to find characteristic polynomials of the matrices. So let's keep it simple, okay? You can always find the roots of a polynomial, but you got to get the polynomial first, right? So we need to figure out what the determinant of A minus lambda I is for that matrix A. So how are we going to do that? How are we going to find that determinant? I mean, let's think about what the identity is. Three by three identity. And you're going to multiply that by lambda. So what's the first thing we have to do to get the determinant of this A minus lambda I? What's the first thing we need to do? What's inside those parentheses? Don't parentheses usually mean do that first? You know, grouping symbols. What's the first thing we have to do with the matrix A and this lambda times the 3 by 3 identity? What do we have to do with those two matrices? Before we compute the determinant, that's right, David, we have to subtract lambda times the identity from the matrix A. Okay, and then we can compute the determinant. Now, for this kind of situation, it's going to be difficult to compute the determinant using row operations and determinant properties. It's going to be much easier to compute this determinant using just straight cofactor expansion. So let's go to the next page here. And there's some stuff that I'm not worried. I mean, since I changed the problem a little bit, you don't need to worry about this part here. So remember, cofactor expansion, you have to worry the cofactors whether you have the plus or minus in front of them. So there's that little nice chart at the top that you're used to. And here's the determinant of A minus lambda I. And I'm doing this cofactor expansion. Actually, I crossed out something I didn't want to cross out here. Hold on. Let me take that back. Okay, so that's cofactor expansion. All right, are we, what row or column are we doing our cofactor expansion along? So, I mean, here's our matrix. There are no zeros in the matrix, so I'm going to have the sum of three, let's say it's the right way. Hold on here. Cofactor expansion, that was back in section 3.1, right? Okay, so I want to know if I'm expanding along the first row or the first column, second row or second column. What row or column do I appear to be expanding along for this cofactor expansion? David's thinking the first column. But if it were the first column, what would, if you think of the little chart, plus, minus, plus, minus, plus, minus, plus, minus, plus for a 3 by 3. If we were going down the first column, in front of that -3, what would be in front of there? Negative, right? And the negative of a -3 is a +3, and we have a -3 here. So good try, David. Good try. It's not the first column we're doing cofactor expansion along. It's the, who can tell me? We appreciate all answers. That's right, Marcella. It's the first row. That's right, the first row. So first row. That's what you're going to get. Now you have 2 by 2 determinants here to compute. So what MyMathLab is going to want is it's going to want a polynomial. So you have to compute those 2 by 2 determinants like you see here. And this here is what? This is 3 lambda plus 6. Make that a little better. Please let me know if you have any questions. All right, may I go to the next page? Are we good so far? David, we're not, let me see. Yes, that's correct. The A minus lambda I, you are taking the identity times lambda. And so since the identity only has 1, it has 1s along the diagonal, all the other entries are 0. You would just be left with lambdas along the diagonal, right, for that. You're welcome. Are there any other questions before we move on here to the, so MyMathLab's not going to accept this answer. Okay, you're going to have to take the 1 minus lambda and multiply it by lambda squared plus 4 lambda plus 4. And then you're going to have to take the minus 3 and multiply it by 3 lambda plus 6. And then you're going to have to take 3 and multiply it by 3 lambda plus 6. So if we do that, we end up with this here. But that's actually not what my math lab is going to want. So let me just go to the whiteboard. Okay, I'll come back to this, but I want to, kind of, let me go to the whiteboard here. And one moment, let me write down what we have. Hold on, everybody. Okay, so we have the determinant of A minus lambda I equals 1 minus lambda times lambda squared plus 4 lambda plus 4 minus 3 times 3 lambda plus 6 plus 3 times 3 lambda plus 6. Looks like we get a cancellation here, doesn't it? That's pretty cool. Those terms drop out. I mean, okay, so now what we have to do is we have to distribute the 1 minus lambda to the lambda squared, the 4 lambda, and the 4. Okay, so that's going to be 1 minus lambda times lambda squared plus 1 minus lambda times 4 lambda plus 1 minus lambda times 4. Okay, and so we're going to get lambda squared minus lambda cubed plus 4 lambda minus 4 lambda squared plus 4 minus 4 lambda and let's see, lambda cubed. Let me just see here. I tend to like to put dots above things when I, like, okay, I've used that term. Now lambda squared minus 4 lambda squared. Sorry, hold on. Sorry, class, I had to shut that down. Thank you. Let me put this on silent here. That happened before, didn't it? That crazy, hold on here. That's my special ringtone, but let me put my phone on silent. I don't want that interfering with our class, you know. Hold on here. My gosh, how do I do this? Okay, put it on vibrate. That'll handle that. Okay, all right. So, okay, back to business here. Okay, now lambda squared minus 4 lambda cubed is minus 3 lambda squared, and it looks like we get cancellation here. And then I guess we have +4. Let me just see here, one moment. Okay, so I think we're good. Does anybody, I mean, are there any questions on this? I'm just checking one thing, class. Hold on. Let me just check one thing. I'm double checking this answer, okay? I'm just double checking this answer. Yes, that's right. That's right. So this is what my math lab's going to want. Okay. Now, to me, I mean, it's fine getting the characteristic polynomial, but what's more interesting to me is getting this characteristic polynomial in factored form. That's more interesting to me because if we can get the polynomial, I mean, ultimately to get the eigenvalues, we have to, you know, we want the determinant of a minus lambda I, which is negative lambda cubed minus 3 lambda squared plus 4. We want to set that equal to 0, right? And so how many remember solving polynomial equations like this in pre-calculus? Do you remember where you had to use the rational root theorem? And I mean, it's not a quadratic equation, so you can't use quadratic formula. It's a third degree polynomial equation. So how many remember, okay, I look at the -1 here and the 4 here and P over Q, and you make a list of possible roots, and then you do synthetic division to test which root is right. Or you could graph the polynomial. You could graph this polynomial and see where it crosses 0, and the x-intercepts would be the roots or the eigenvalues. I mean, how many recall doing these kind of things in pre-calculus? Yeah, Mikhail says it's familiar. It's familiar. And David, you don't recall that? Solving a polynomial equation, finding the roots of a polynomial equation? Oh, okay. All right, David. Well, but I assure you, you would have seen it. I assure you. So, but this is really, I think for my math lab problems, they just want these, they want the polynomials in simplified form. They want you to multiply everything out and actually give them the polynomial. I can tell you that if and then otherwise for third degree polynomials, they'll tell you what the eigenvalues are. But I can tell you that this characteristic equation here factors as negative times lambda minus 1 times lambda plus 2 quantity squared. So this means that you have two eigenvalues. One is lambda 1 equals 1, and what's the other eigenvalue? That's right, lambda 2 equals -2. And eigenvalues have multiplicities to them. So the lambda minus 1 factor occurs to the first power. So lambda 1 equals 1. That is an eigenvalue with multiplicity 1. But the -2 eigenvalue corresponds to the factor with the squared power. So that has multiplicity 2. Okay, so do you remember like roots have multiplicities in polynomial equations? I don't know, maybe give me a thumbs up if you've heard that before. Well, what'll happen, Mikhail, is I think, okay, all right, well, that's okay. So multiplicities mean how many times does the root occur? And in the polynomial equation. And in your homework for like characteristic polynomials of second degree, you can use quadratic formula to get the roots. But for for characteristic equations or characteristic polynomials of third degree or fourth degree or higher, they don't ask you to find the eigenvalues. But yeah, you could use Desmos to get the eigenvalues, but I don't think in the homework they ask you because they, again, this book, it's a great book, but it was written back, before there was Desmos and all that, and so to find the roots, people had to actually use that rational root theorem, which I'm sure most of you have seen. It's just been a while, but there you go. There you go. Are there any questions on that problem? All right, let me point out a few things here in the book, and I want to do another example too. Let's just get through these great examples here. So, example 3 in the book. Okay, so look here. Now here, what's the size of matrix A in example 3? How many rows, how many columns? It's a square matrix with how many rows, how many columns? That's right, 4 rows, 4 columns. Now we had kind of it was a little bit of work to find using cofactor expansion to find the determinant of a 3x3 matrix. Now we have a 4x4 matrix. But what's interesting about this matrix A here, what is interesting about it? That's right, it's triangular. Is it upper triangular or lower triangular? All the zeros are below the diagonal, so that's right, Mikhail. It's upper triangular. And remember, to find the determinant of an upper triangular matrix, what's the only thing you need to do? To find determinants of upper triangular matrices or lower triangular matrices, all you have to do is, hold on here, multiply, that's right, David, multiply the diagonal entries. And so that's what you do. And the eigenvalues, yes, are 5, 3, and 1. That's right. So for this kind of problem, you can just read off the eigenvalues based on the, based on the characteristic polynomials. So what I'm trying to say is, I guess MyMathLab will have you say, hey, find the eigenvalues for a characteristic polynomial or a characteristic equation of degree 3 or more. but it's going to be something simple where you can, usually it'll be like a triangular matrix. Okay. And then, of course, if you expand these factors out, you're going to get this. And they talk again here about multiplicity. So in this example, 5, or the eigenvalue 5, I'm going to highlight this whole thing. The eigenvalue, hold on here. The eigenvalue 5 in this example 3 that we just looked at has multiplicity 2, because there are two factors that have roots of 5. And the multiplicity of an eigenvalue is its multiplicity as a root of the characteristic equation. Are there any questions on that? All right, let's do a little bit more here. So example 4. Example 4. They have a characteristic polynomial, find the eigenvalues and their multiplicities, and they're having you factor the polynomial. But again, this polynomial is very easy to factor. So in your homework, you should, if it says factor a polynomial, it should be easy to factor. And it's a 6-degree polynomial, so there should be 6 factors, right? 6 factors, and there are. And eigenvalues are 0, 4, 0, 6, and -2, with multiplicities 4, 1, and 1 respectively. Okay, is that, are there any questions on that? Okay, let's keep going then. Another thing we have to mention here is matrices that are similar. Okay, so if you have two square matrices A and B, they're similar if there's an invertible matrix P such that B equals P inverse times A times P, or A equals P times B times P inverse. Okay, we say that the matrices are similar if A equals P times B times P inverse. And similar matrices have a property that's very nice, okay, by theorem 4. If you have two matrices that are similar, they're going to have the same characteristic polynomial and therefore the same eigenvalues. Okay, that's a property. That's a property of similar matrices. The proof is very easy on this. They have a proof here of this. I'll just highlight it. So if you, what you would want to do is show that the determinant of B minus lambda I equals the determinant of A minus lambda I. And they show here how that works. But effectively, you have to use properties of determinants and so forth. I'm going to let you look at that proof, okay? I'm not going to worry too much about that because I want to get to another example here before we go on break. I want to get to another example. But all right, let's. Okay. Very important example. Let me give you a moment to copy it down. Actually, you know what I'm going to do, class? I think what I'm going to do is let's take a break. Let's take a 10-minute break. And we'll look at this example when we return, okay? So let me go ahead and stop the recording here.